This recording is for the Sensation mini lecture that was given on Tuesday, October 20th. This is a fairly short recording because obviously I won't be going through the demonstrations, just the content. Sensation and perception are two things that are interconnected. Sensation is the idea that our sensory organs, like our eyes, ears, nose, mouth, etc., they are able to collect information in the form of light energy and sound waves and bacteria and sensations, and then convert that information into electrical signals that the brain will understand. Perception is how the brain makes sense of those electrical signals, how it interprets it, and how it uh, processes it so that we understand the nature of reality. We Sensation perception work in one of two different ways. For things that are new experiences or when we're really young, we use primarily bottom up processing, which is where we sense the basic features, the basic characteristics of any sort of stimuli that's like a sight, sound, touch, taste, or smell. And then our brain integrates those characteristics together to understand what we're seeing. But on the other hand, when we get older, we've experienced most of the stuff that we're going to need to experience later in life. And in that case, we use top down processing, where our previous experiences and our expectations are used to recognize those basic characteristics of the stimuli. So, unlike bottom up processing, where we just take in those characteristics and make sense of them, with top down processing, we take in those characteristics and use our previous experiences or use our expectations to identify what those characteristics are. Like in the case of Fraser's spiral, which is not actually a spiral, just a collection of circles. It looks like a spiral because we have previous experiences with a spiral. And so we perceive it to be a spiral that way, using our top down processing. But if we use bottom up, we would see that it's just a bunch of circles. Whenever a stimuli hits one of our sensory organs, it needs to be intense enough for us to register it 50% of the time. This is called the absolute threshold, which is the minimum amount of information that we need to register a stimulus 50% of the time. Now, sometimes, though, our absolute thresholds are not always the same. So sometimes we may be able to hear better, or sometimes we may be able to hear worse. This is due to signal detection theory. Signal detection theory says that we our absolute thresholds can change due to three things: attention. So if we're not paying attention, then it's going to be harder to recognize the signal. Motivation. If we're motivated to hear a specific stimulus, like the sound of a baby crying for new parents, then we're going to actually have better absolute thresholds, but only for the baby crying. And then the third one would be expectation. If we expect that a signal is coming, then we're going to be more attuned to that stimulus and that signal. Now, whether or not we experience that signal depends on our overall attention and how we recognize the stimulus. If there is a signal out there, like if there is a stimulus and we recognize it, we would call that a hit. If there is a stimulus and we don't recognize it, we would call that a miss. If there is not a signal, like there's not a stimulus, but we think there is, like for example, when you check your phone for a text message, even though nothing has happened on your phone because you think you heard it or you think you felt it, that would be a false alarm. And if there's no signal and we don't register anything, that's a correct rejection. Now, along with absolute thresholds, we also have difference thresholds. Difference thresholds are the minimum amount that we need to notice a change. And this is sometimes called the just noticeable difference. So, like, for example, when we go from volume level 15 to volume level 18, we notice a difference in the volume of a sound. But Weber's law says that that difference is not a specific amount, but instead a specific percentage. So that it's a logarithmic scale, meaning that uh, there needs to be a specific percentage increase for us to recognize the difference in a stimulus. So, for example, when you go from volume level 6 to volume level 7, you will probably notice a difference. But when you go from volume level 30 to volume level 31, you don't, because it's not a big enough percentage increase. In this diagram, we see a passage which grows bigger with each line, but we don't actually recognize that it grows bigger until about midway through, due to it being enough of a change for it to cross our difference thresholds. This disappearing circle illusion shows something that we call sensory adaptation, which is the idea that when we first experience a stimulus, we experience it strongly, but later on, our senses adapt to that stimulus and we don't feel it as strongly and sometimes not at all. Like, for example, when you go into a room and you smell a weird smell, but then 30 seconds later, you don't smell it any longer. Our eyes are one exception because our eyes are constantly keeping things in focus. So while we can have things disappear, like in the disappearing circle illusion, at least temporarily, it will not be permanent because our eyes are constantly shifting so that our field of vision doesn't just go completely blank. Additionally, when we experience things, stimuli through our senses, we can also have that experience be interfered with by other brain processes. This is called sensory interference and is best demonstrated through the Stroop effect test, where in this test, what we see is that we are sensing the color, but yet when we try to communicate what we're sensing, our processing of reading is interfering with our ability to communicate. So if we tried to say the color of the word in row one and we said red, it's because we're reading it rather than saying green, which is communicating the color. Finally, when we experience a stimuli, we may focus on it really, really heavily. This is called selective attention. This allows us to obtain all the characteristics and all the features about it and all the unique properties of that stimulus. But what it might make us blind to is other things, other stimuli. If we're paying too close of selective attention to one stimuli, it may make us blind to other stimuli, and this is referred to as inattentional blindness. Finally, the last concept is that as we take in these these stimuli, our sensory organs are taking in raw information, light energy, sound waves, bacteria, and those sensory organs all need to convert them to electrical signals that the brain can understand so that we can perceive what it is we're experiencing. It's only through transduction that this occurs. Transduction is the process of converting the raw information, the light energy or sound waves or, or chemicals, into electrical signals that the brain will understand. And this is where we completed the lecture.